All right, I'm Nicoletta Mino, and today Brian and I are here with Andrew Dereka, Product Manager at Laird Thermal, and Vineet Barot, Technical Support Manager at Thermal Products at Sager Electronics, and we are going to talk about thermoelectrics. So thank you, Andrew, and thank you, Vineet, for joining us today. We appreciate your time.
Sure thing.
Yeah, happy to be here.
Awesome. So let's dive right in and talk about thermoelectrics. At the very highest level, what are thermoelectric coolers and how do they work?
Yep, so thermoelectrics are very small heat pumping devices. Most of the products can fit in the palm of your hand. Some are so small they can actually, or can be laid onto a fingertip, or even can be as small as a pencil point. Basically, they transfer heat from one side to the other. They use a unique thermoelectric semiconductor material that has good thermal insulating properties and good electrical properties to drive current. And essentially, when you power it, it moves heat from one side to the other. So there's many applications for these products that are used in the low heat pumping capacity range.
So speaking of those applications, what are the applications that thermoelectric coolers are mostly used for?
So it's a very broad market. Our products are used in industrial, consumer, automotive, telecom, medical, analytical spaces. It's one of the fun things about the product. Some of the more interesting ones would be, I'd say, in the refrigeration space. So there's a lot of thermoelectric coolers that are used to cool small compartments in analytical instrumentation or in the medical diagnostic space. If they've ever had any blood work done, a lot of those reagents that mix in with the blood need to be cooled or else they go bad, and they'll use a small thermoelectric assembly unit to cool those. There's also other applications. You have a lot of spot cooling applications. So the optoelectronics market is really fascinating right now. There's two branches there. One's in the automotive sector where you get into this electrification of the vehicles, and there's all kinds of cool technologies that are going on the automotive space. So they'll use thermoelectric coolers to be able to essentially keep those optoelectronics from overheating. And then similarly in the telecom space, there's a lot of optoelectronics that are used in the datacom and telecom market space for high-speed transmission. There they would use thermoelectrics for the same reason, for temperature stabilization of lasers.
So Andrew explained thermoelectric coolers. The way I like to explain it to a lot of my customers, just in a very surface level, is I show them the actual piece. This looks like a little ceramic piece here, and there's two wires coming out of it. When you put a voltage across these wires, one side becomes hot, the other side becomes cold. So that's very different, because most people, when they're hear coolers, they're thinking about liquid cooling, air cooling, fans, heat sinks, etc. This is a totally different type of product where it's active in the sense you're putting voltage, you're putting current, you're putting power into it, and one side's becoming hot, one side's becoming cold, which gives it very unique properties. And one of the questions that I always get, Andrew, is like, when they first see it, Laird Thermal has a great little demo box that that a lot of people at Sager have, a lot of our power sales engineers have, and we show it to our customers, and they love it. And the first question that I get is, "Great, can I just use this to cool every single device that I have in my board?" And the answer is usually, disappointingly, no. That'd be great, Andrew, if we could supply it for every single product.
On it.
And I don't know if you want to just briefly explain why I couldn't just use this to cool like a CPU or something in my computer.
Yeah, so definitely the product itself, you want to use it below ambient. A lot of customers, I would say, want to use it, but if they don't need to go below ambient, there's really no need to use it. It's quite an expensive product. Typically requires temperature control and going into a closed loop feedback type system. And some things like heat sinks and fans can basically just do the job quite well. So key is really you need to go below ambient. There also is limitations in terms of heat pumping capacity. So the product's great when you're trying to remove watts of heat or tens of watts of heat, even hundreds of watts. But when you start getting into that kilowatt range, there's really other technologies out there like recirculating chillers, compressor-based systems that just work much better than the technology.
Yeah, because most chips, they might be rated for a junction temperature of, let's say, 125 degrees Celsius. It's pretty common. Or even you might have LEDs that you might want to keep under 80 degrees Celsius. But you know, even the hottest weather, you're not going to be above 45, 50, 55 degrees Celsius ambience. So you always have that positive delta. You always have the chip can be hotter than the ambient. So there's no need to introduce additional power through a TEC thermoelectric cooler. And all the other reasons that Andrew talked about, you know, heat pumping and all of that.
Unless
So that's,
unless you're a
yeah.
crazy gamer, Vineet, then those
Unless-
those guys are using thermoelectric coolers to improve the clocking speed, and they don't care about power. They're willing to put as much
Really?
juice into the computer as possible. Sure.
Oh, I didn't
Yeah,
know that. Okay.
we sell TECs into that market space. It's pretty nichey, but for the really high end gamers, they will take TECs, mount them onto a liquid cooling solution, and they'll get that
Okay.
temperature of the GPU down to give them that little extra edge when they're playing their games.
You're giving Brian some ideas now.
Yeah, I know. Well, you talked a lot about the factors, right? Are there other factors that should be considered when deciding to use a thermoelectric cooler in your application?
Yeah, sure. So, I guess so. Size factor we really haven't talked about, but in general, the product itself, like I said, usually fits in the palm of your hand. So typically, there's size limitations because our products are mounted on ceramic substrates, and if you go too big, they tend to crack. Then there's also secondary factors that you need to consider, and that's how you mount the product itself into the application and some of the finishing options per se with how you provide power to the product using lead wires, sealant. If you go below dew point, there's things you need to be concerned about with condensation. So just like with general electronics, there's things that you need to do to assure the product is robust and optimized for the application.
Well, you brought up gaming before. Are there any other surprising applications that people wouldn't think about for thermoelectric coolers?
Yeah, some cool one is in the virtual reality. So you put on the goggles and you can see this virtual world. Some of the interesting things is embedding thermoelectrics into the goggles themselves. So
Okay.
it adds a heating cooling element. We don't supply into that market, but I thought that was one of the cooler type applications that I've seen. Going back to automotive and the autonomous system space, I think LiDAR is a really cool technology that's being commercialized and deployed as we speak into that market. So that's pretty exciting. So those LiDAR systems will use TECs to basically temperature stabilize the laser. So as the laser is shooting out and creating all these data points on the 360 mapping, that wavelength can change as temperature changes. So to keep that temperature stable and assure you get a good laser rebound coming back into the system, basically they'll use TECs to keep them cool. So there's hundreds of neat applications in this industry.
So what are some of the other main advantages of using thermoelectric coolers for to compared to other cooling technologies, right? You talked a little bit about that, but what are some of the advantages?
Yeah, so biggest competitor probably would be with compressor-based systems because those products also go below ambient, and the key difference is form factor. So with thermoelectric coolers, you can go so much smaller than you can with a compressor-based system. It's lighter. It can be mounted in multiple orientations. It's cheaper. It's way cheaper than a compressor-based type system. And it just finds that niche in today's compact cooling applications. And as it's almost like every market, everybody wants to go smaller, and it's very conducive to using thermoelectrics. They also operate on DC voltage, so there's plenty of access to 12, 24 volts. A lot of these medical or analytical instrumentations that use that, so it fits right into those applications.
You basically talked about all three of these applications, but one of the advantages is also switching is so much easier, right, Andrew? As opposed to a compressor-based system, if you want to do heating and cooling, and you have to switch from the cooling mode to heating mode, it takes a little bit of time for that switching to happen, or you may have a totally different system, one for the cooling and then a heater for the heating portion of it. Big advantage of these TECs is you literally just flip the current, and one side, it switches which side is hot, which side is cold. Might be a good time to just back up and talk about the three applications that Andrew already mentioned, but these are the three that I always tell customers. One is going below ambient. That's the one we talked about. So if you're air cooling, you can't go even close to ambient, let alone below ambient, right? Heat
Right.
transfers from hot to cold. So you can't get your device, no matter how many fans you put on it, it can't get lower than the air temperature.
Mhm.
The other one is the switching. So switching from heating to cold, like the LiDAR application that you talked about, Andrew, you might have to keep the LiDAR at, let's say, 28 degrees Celsius. Well, it might be colder than 28 sometimes. It might be hotter than 28 other times. So you have to switch those into those two. And so I kind of mix those two, but basically temperature stability and switching, you can think about them as different applications because some applications require heating and cooling and others require stability, even though it might technically get both of those using the same kind of switching. They are, you can categorize them as two different applications. But you talked about voltage, Andrew, and one of the questions I always get is like, oh, well, I only have 10 volts, or, oh, this is a 12 volt. Do you have a 24 volt? If you're operating a fan or something like that, you have a very narrow range. If it's a 12 volt fan, it might work from 10 to 14 volts. And it's, there's a slight variation in the fan speed, but roughly it's like you're meant to run it at 12 volts. TECs don't quite work that way, right?
Yeah, that's right. So essentially, the product itself, it's designed to have many NNP couples in there. And the more NNP couples you can put in between a thermoelectric cooler, the higher the voltage rating is. So we definitely try to design the number of couples under a thermoelectric cooler to match a 12 and 24 volt, because that's typically what you'd see in a lot of the medical, analytical, even some of the telecom applications. Where it gets a little bit more challenging, I would say, is when you do really smaller modules, because there you can't fit the proper number of couples on a thermoelectric cooler to get to that 12 volts. So there you might have half the number of couples. You might be at 6 volts, or you might have a quarter of the number of couples. So you might be at like 3.1 or 3.3 volts. But the uniqueness with thermoelectrics is that you can add number of couples on a thermoelectric cooler to come up with a particular voltage range that the customer has available to use.
Okay. And Andrew, on the voltage, how are you actually controlling the module? Are you controlling the current? Are you doing PWM? What's recommended controls?
Yeah, most of the time that we see in the market is the PWM. So I'd say most of the time our customers are driving the thermoelectric cooler. We'll either have the thermocouple onto our device, which will give it that closed loop feedback control. And I'd say PWM is a very good way to go. It's a very cost effective temperature control solution.
Yeah, Andrew, it makes sense about the PWM control. On fans, they list very specific frequencies. Are there some frequencies that customers should be thinking about when they do these controls?
So it's not a core area for us. We generally
Okay.
sell thermoelectric coolers or thermoelectric modules. We do have some temperature controllers, but most of the time customers will take that temperature control portion and put it into their board that's also driving other things throughout their instrument.
Yeah.
And the big question we always get is what frequency does it operate at? Because if you run at too low frequency, it can act as a on off, and that's essentially stressing the thermoelectric cooler. But if you run it at higher frequencies, then you kind of minimize that impact to the durability of the part itself. And if you go too high, then you run into EMI issues. So you kind of have to find that sweet spot on that frequency. That's typically what we get asked. Outside of that, they generally have a good electrical engineering team that has that expertise in-house, and then they'll just tell us, this is the thermistor we use for these other projects we've had great success with it, and we'd like for you to use it in the assembly that you provide us, something like that.
Andrew, what about just a straight up voltage control, just changing voltage, or is that
So you're
an
talking
all
about
right
like
way
a
of
power
controlling it?
supply and
Yeah, just a power supply that changes. Yeah, with
you
variable
certainly
voltage.
can, I guess. How do you get the feedback loop to that?
So if you have it set up, yeah, you'd need some sort of a PID loop or something that tells
In
you
the lab,
temperature versus
you
voltage.
can certainly do it, and we've done it many times.
In the lab, okay, but
Yeah.
in most applications, it's probably going to be PWM controlled
Yeah, that's right.
of some kind. Okay, understood.
Now, how are you? I guess you mentioned different types of voltages, right? With the thermoelectric coolers. Now, is there difference between, you talked about mobile apps and you talked about non-mobile apps, right? You talked about, is there any difference in the way or what engineers need to look for instance, they have a drone with lidar versus, do you know what I mean, some lidar in a ground penetrating system or something that may have its own power, you know?
Yeah, so definitely with mobile applications in general, the big thing is lower power consumption. So you bring up a great point, Brian. Thermoelectrics can be power hogs, and they can kill the life of the battery.
Right.
So we get pressed as an industry to really come up with thermoelectric coolers that minimize the power consumption. And we can do that to a point. So we can tweak. So in the thermoelectric cooler, there's we call them dice or thermoelectric elements. I like to use the word dice, but basically there's dice. They have N and P, and that'll create the couple that I was stating. So you can alter the geometry of those thermoelectric elements to basically be matched in the customer's application so that it consumes the least amount of power. And that's what we try to do in those applications. But yeah, believe it or not, we've sold TECs into drone applications.
Right.
So that's pretty exciting market out there.
Mm-hmm.
Well, you raised a point that, this is something that, the industry challenges you to do. And I was wondering if there were any other challenges or limitations that thermoelectric coolers are currently facing, that engineers and scientists are trying to work through now.
Yeah, so depending on the application, we're always being pushed for higher performance. So that can be higher heat pumping capacity. We're being pushed into doing miniature form factors. And I think one area that we probably haven't talked that much about is really in the thermocycling space. So there's harsh environments. When you expose electronics to heat or heat cool, it's really damaging to electronics. But in the thermoelectric industry, they expect your stuff to last forever. So you have to come up with very robust thermoelectric coolers, and we do have technologies on the way we build the construction of these parts and the way we seal them to help have them survive these really harsh environments. So I just want to mention really quick on the thermocycling space, PCR, that was a super hot topic back in the COVID era. And most of those machines will use thermoelectric coolers to be able to heat and cool the DNA sample with the biomarkers in order to be able to make a call on if you have COVID. And that machine is used for other applications, but that was just a hot one back in the COVID day. So that thermocycling is extremely stressful to thermoelectric coolers, and there's very few companies in the world that can make a really robust thermoelectric coolers to survive in that application for a long period of time.
So let's talk about materials, for instance. Now, what are the thermoelectric coolers made of? And have there been any advancements in like the material science or manufacturing that have helped the performance of the thermoelectric coolers?
Yeah, sure, definitely. So it's come a long way. The material properties of the thermoelectric material works great in only one direction. And so we try to go to make the material operate great in the Z direction, because that's typically where you want very good thermal insulating parameters. The main components is bismuth telluride. Those are the main elements that are used in there, and there also is some other elements that are in there in very minor amounts, but that's still the main ingredient. And the reason why it's still used is it works great in temperature ranges from 0 to 200 C. That's kind of has very good thermal insulating and electrical conductive type properties. So in terms of advancements, there's a lot that's been done on the manufacturing side to be able to squeak out that performance. And I would say it's more incremental gains. You're not going to get something that's going to get 20, 30%. That's only at a university in a research paper, but trying to commercialize that is a total nother story.
Yeah.
But yeah, there's definitely things that we have done as a company to help incrementally improve our processes to produce really great materials.
Yeah, Andrew, this material, when you first feel it, it just feels like ceramic, which, it is ceramic on the lids. And it can be not fragile, but, we're not dealing with metal or, malleable plastic and other things that you would normally deal with in the rest of the electronics. So it can be, it can seem like a challenge to package these and actually apply them. I know Laird Thermal does a great job on their website They have some calculators I'd love to talk about. Then also just in terms of application guidelines and packaging. And one of the things that you guys recommend is, putting a decent amount of pressure on these when you're packaging it. So, whether it's between two heat sinks or what that might be, which seems like a challenge. You have a ceramic piece and you want to put good amount of pressure on it. Is there some secret sauce to when Laird Thermal makes an assembly out of these modules? Is there some secret sauce that you're using, or is it just about following the instructions and taking good care when you're doing the packaging?
So with the thermoelectric cooler, you want to be able to clean the outside surfaces. You also want to be able to clean the surfaces on the heatsink. You also want to make sure that the mating heat sinks have very good polish finish to them and flatness surface. And then also on the interface material. On the interface material, you want to be able to make sure you can apply a thin layer because that bond layer, the thicker it is, the worse the performance. And that's often a mistake that a lot of our customers make, where they're into these greases that are very thick. They have high thermal conductivity, but the distance between the thermoelectric cooler and the heat sinks is spread so far apart that actually worsens the performance.
So
And then
it's like, should you be using thermal grease or thermal paste, or is there something that you need to use specially
for
for?
larger form factors, we definitely recommend using thermal grease. And the applications I'm thinking about are more on the refrigeration side. There's certain applications where you might be thermocycling and their grease may not work, right? Because it'll pump out with the changes of heat cool. So there you might want to switch to something else like a graphite material, which also has great lateral heat spreading. But for the most of the part, for large form factor thermoelectric coolers, you will want to use thermal grease.
I have kind of a two-part question. First part is, over the past decade, let's say, how have you seen the market change in this way?
Yeah, so it's changed quite a bit. So there's a lot of new materials coming online per se, not necessarily at the composition side, but with the processing side. So there is a few players out in the market that have really superior performance. There also is higher level of construction methods that are done in the industry. So there's really high performance assembly to really precise placement that's going on. And I'd say that's pushing more into the miniaturization type area. Things have gotten so small, so fast. It's really unbelievable. But particularly in the telecom, datacom space, things that used to be 10 by 6 centimeters was fine, and now they want to get down to stuff that's like 2 by 2. It's really incredible. And we used to have thermoelectric elements that were size 2 by 2. So it's really incredible how small, how quickly the parts have gotten in the industry. And then also just from a robustness perspective, there's applications out there that need to survive high temperatures. So you need really good construction methods for those applications. And then you have other applications where you're doing this high thermocycling, and nobody wants to settle with existing heat pumping capacities. Everybody wants higher heat pumping capacities, or what we refer to heat pumping densities. So there's multiple facets of this that just keeps pushing us further to do higher level of process capability, higher level materials development to really keep up with the customer's requirements.
And also temperature differentials, right, Andrew? I don't know if that you'd include that in heat pumping capacity, but you have a lot of modules that are double stacked, for example, to get you to really higher temperature differentials. Because there is a limit, you can't use one TEC module and expect to get like 50 degrees C below ambient or something like that, right? What are some of the higher end, like a stacked module, for example? What are the highest like delta T's it might get to?
Yes, sure. So definitely on the single stage modules, and it always depends, right? It's based on what the hot side temperature is that the cooler is attached to and what the heat pumping capacity requirements are. But in the vacuum, you can get to very low temperatures. So from a room temperature environment, getting down to -50, -60 C is no problem.
Wow.
But the
Wow.
reality is there's almost also no heat pumping capacity as well.
Right.
So
Yeah.
if you start adding heat pumping capacity, you'll get nowhere near as that minus 50 or minus 60 range.
Yeah.
The multi-stages is another interesting product area. It's an area we haven't really discussed today, but they're an image sensing. Multi-stages are really important. So just for Brian and Nicolette, so most of our products that we sell are single stage. Across the thermoelectric cooler itself, you'll get a temperature differential of about 70, 74 C. And in reality, when you put it in the application and the heat load, you're probably half that. So you'll probably be at 35 C. So that means if you're in a room temperature environment at 25 C, you'll get to 0 or 5 C with the thermoelectric cooler.
Yeah.
With the multi-stage that Vineet's talking about, there you're actually stacking stages one on top of each other, and each stage has a temperature differential. So in these more high-end imaging applications, like for example, border security, we're trying to look at 10 kilometers or more with an infrared type system. That's a perfect example of an application where the IR sensor is going to use a thermoelectric cooler, and when you keep it cool, you minimize the thermal noise, and this helps the IR sensor capture a more crisp image resolution, and those products are used there. So there you can cool, depending on the quality you want, anywhere from minus 20 to minus 60 typically in those environments.
And that's where I mean, you talked about packaging before, and just packaging a TEC in a heatsink. If I wanted to duplicate a multi-stage, probably not a good idea to take two single stages and stack them on top of each other.
It has been done,
Okay.
but the problem is you have that additional ceramic layer, and you lose a lot of temperature differential, and you lose
Okay.
efficiency. So multi-stages are really typically power hogs. So you want to take every design technique you can to make them as efficient as possible.
Yeah. And you mentioned delta T versus pumping power. It's basically just like an inverse relationship, right? So if you want very little temperature differential, it can handle a very high heat load. If you want a high temperature differential, it can't really handle a very high heat load.
That's right.
Almost opposite, which is, one of the things here is I've been doing thermal engineering for a very long time, and a lot of air cooling applications, liquid cooling applications make sense. You can do the math. When it comes to TECs, the math gets really complicated really quickly. And one of the ways that I recommend engineers go on Laird Thermal's website, it's one of the best websites I've seen. Every single page on every single product has its own calculator that has built-in properties. You can, you can set the sliders. You can put in your application, and it'll tell you what to expect. And then they also have calculators for different applications. So whether it's electronics enclosure, which is what a lot of Sager electronics customers deal with, or a thermal cycler, and I'm sure I'm missing many others, Andrew, but there's a lot of different application pages. You can go into those and change the different settings, and it'll give you, here are some products that could work with you. I think it's very neat, very cool to use, but it's also can be daunting for someone who hasn't really dealt with it before. So that's definitely something that myself or anyone at Laird, like Andrew, can help you out with if anyone needs it.
So I have a question. Can an engineer buy an individual module with a custom heatsink?
With a custom heatsink. So this is where the partnership between Sager and Laird works out really well, because Laird Thermal does have a lot of assemblies, what we call TEAs, thermoelectric assemblies. So that can be a heatsink on one side, it can be a liquid cooled cold plate on one side, or it can just be direct cooling, just a plate that's going to get cold. You could use it for cooling whatever else you might need to. So you can think of the three combinations: so air cooling, direct, and liquid, and you have two sides of it, right? So there's different combinations and different sizes. So there's a lot of options on Laird Thermal. And Sager, we stock both the individual modules and the assemblies. However, as to your point, Brian, there's always some customization that's needed. Either somebody wants a different voltage fan, somebody wants a larger heatsink, smaller heatsink, etc. And what we'll do is we'll work with Laird, and we'll work with our other thermal partners that make heat sinks, make cold plates, make fans, and customize it at our custom solutions center in Texas.
Okay, I'd like to circle back to the second half of my question, if that's okay.
Yes,
So
please do.
we talked about the changes over the last 10 years, but what about the future 5 to 10 years? How do you see thermoelectric coolers evolving in the next, decade or so?
Yeah, I just think it's going to continue on that same trend. The one thing I guess I didn't bring up was cost. So customers will be pushing us, and over the next 10 years, for smaller form factors, for higher heat pumping densities, lower power consumption, and lower cost. That's what the future is. It'll be interesting to the point because the parts are getting so small. You almost have to remove the ceramics now at this point if you want to get smaller.
Wow.
It's be interesting to see if they get to a point where they actually integrate just the thermoelectric elements themselves into the designs.
So, Vineet, you mentioned the Laird calculators and things like that is a good resource. Are there any other resources that the audience should check out for more information?
Definitely a lot of application notes that are on Laird Thermal. Either there's white papers, and there's also just here's how to package a TEC. There's lots of those things as well. I would definitely recommend keeping those the 3 applications that we talked about. If your electronics or other type of application needs any of those 3, which is going below ambient temperature, cycling between hot and cold, or maintaining a stable temperature with varying ambience, then that's when you want to start thinking about it, and we can help you get started there.
Yeah, I'll just comment that distribution is a really vital role. A lot of customers are new to thermoelectrics, and they will best thing is just to try it, buy samples of parts, think about how you plan to use them, and try it and see what happens. That's always the best way to get into a new product area.
And that they could do at Sager, right, Vineet?
Absolutely. We'll be happy to sample you some products to try out. You have to try these. I mean, they're fantastic. We see you in person next time. I'll bring the sample, Brian and Nicolette, and you guys can see what it feels like.
Thank you for joining us today, guys.
Yeah, thank you for having us. It's a pleasure.
Yes, thank you.